This is the third and final part of a workflow that uses a delta function to scale the isotropic velocity model to a vertical velocity, in this case derived from well checkshots or VSPs. If you have not seen parts 1 and 2, look for them in the Doug Learning section of the online help first. To recap, this project has a 3D survey and 5 wells, linked by this arb line shown here. The current display is in two-way time, with wells displaying gamma ray logs. Our reservoir interval is from the top M to base res horizons, which have both been thickened and coloured brightly to make them more visible. After calculating a delta curve for each well using the synthetics tool, the interpolated delta model has been applied to the isotropic seismic interval velocity to create a calibrated velocity volume that matches the well checkshots. This final part of the workflow introduces some tests to help you decide how good the final calibrated volume really is. Making the velocity model is simple, but it is important to check the model is valid. One of the first things to check is the time to depth conversion. The dynamic conversion is currently configured to use the original uncalibrated migration velocity, and it is possible to visually flip the section from time to depth. Here, the well markers tie the seismic in time, but in depth there is a mistie, because the migration velocity applied to the horizon and traces is faster than the checkshot velocity applied to the markers and logs. To see the calibrated V0 velocity conversion, I need to configure the time depth conversion with the V0 volume. The calibrated V0 velocity is calculated on the fly from a process derived from the active velocity conversion, and so to avoid creating a process loop, I must first output a static copy of the calibrated V0 volume. Click on the Volume tab, select the calibrated V0 volume and export. Select the default name, which matches the process name, and remember to add the volume back into the session. After configuring the time to depth conversion with the calibrated velocity saved to disk, the depth section updates and creates a much better tie seen here. To see how much difference there is between the two depth conversions, I could use horizon maths to compute and display both depth surfaces together. After displaying the base res horizon in time, select Horizon Maths Operations. Add the horizon and select the depth attribute computed from the active time depth conversion. The formula is simply the input horizon, and then calculate creates the results. Rename the resulting horizon appropriately. That's the horizon depth converted using the calibrated V0 velocity volume. Now change the time depth conversion to the original migration velocity. The calculation remains the same in Horizon Maths. Create the new horizon and rename appropriately. That's the depth converted horizon using the migrated velocity volume. In the section view, the new horizons are not very visible, so I'll make the colours brighter and thicker. There is quite considerable shift of 100 to 150 metres, confirming how important it is to use the correct velocity. Tests can be run on the model to evaluate different parameters and components. When constructing the volume, there was an option to smooth the log delta functions in the synthetic tool. A 48-metre smoothing window was selected to make the curve less blocky. The model can now be updated to check the effect of using a smaller or larger smoothing window. First, a smoothing value of 12 metres is applied. This is the Insight default and is less than the default 20-metre sampling, so the log is effectively unsmoothed. The change looks significant compared to the delta log smoothed at 48 metres, and so the updated V0 calibration is exported to a disk volume and added to the session. Next, a smoothing value of 96 meters is applied, which is double the value used initially. The change looks significant to the delta log, and so the updated V0 calibration is also exported to a disk volume and added to the session. The versions of V0 are arranged in order of increasing smoothness in the control panel to aid selection for comparison. Returning to the section view, the results of different smoothing can be observed in the final depth conversion. Here is the depth using a default 12-meter delta curve smoothing window. Here is the depth using the chosen 48-meter smoothing window. And here is the depth using a 96-meter smoothing window. The results show there are some very slight changes between the smoothed input curves, but nothing of a significant impact. Another useful test is to remove an input data component to see if the model improves or not. Here, the well 11 shows a slight mismatch, and so will be the first well to be removed. Setting the original velocity for depth conversion, the delta model process can once more be updated. All that is required this time is to delete well 11 from the input list, after which the updated volume must once more be exported to disk. Selecting the velocity including well 11 first, then updating to the velocity without well 11, it is clear that the depth tie and therefore model has improved. This suggests a possible issue with the input data from well 11. It's great to have identified this issue early on. The well can now be left out of the model for a quick result, or the raw logs checked again for any problems causing the shift. Removing the other wells one at a time will demonstrate how much contribution each well adds to the final model and therefore its individual importance. That should keep me occupied for a while. Please note that both the V0 and delta models were created in the two-way time domain for this workflow. If the velocity is required in the depth domain for depth migration, the V0 model can be converted to interval velocity depth using the velocity conversion process. This conversion is demonstrated in one of our other tutorial videos in the learning section.
If you have questions or would like to discover more, then visit our website at www.doug.com. And remember, have fun with Insight.